So let's continue with the Stack and Queue playlist. Today for starting off, hey everyone, welcome back to the channel. I hope you guys are doing extremely well. So the problem that we will be solving today is sum of subarray minimums. So what is the problem stating? It is stating that you will be given an array of numbers. Now your task is to tell me the sum of subarray minimums. Let's understand. So given an array, if I end up writing all the subarrays possible. So maybe I'll start off with the first one, which is 3. 3 is an individual element subarray. And then maybe 3, 1. Then maybe 3, 1, 2. Then maybe 3, 1, 2, 4. So these are the 4 subarrays that start with 3. After that, maybe I can write 1 and then a 1, 2 and then a 1, 2, 4. So these are the 3 subarrays that start with 1. After that, 2 and a 2, 4. These are the 2 subarrays that start with 2. And after that, 4. So what I've done is, I've written down all the subarrays possible from this particular array. Now, your task is to figure out the minimum, if you see properly, the minimum of all the subarrays. Can I say the minimum of this is 3, the minimum of this is 1, the minimum of this is 1, the minimum of this is 1. Quite simple. 3, 1, 2, 4, the minimum is 1. Of the entire subarray, give me the minimum. The minimum of this is 1, the minimum of this is 1, and the minimum of this is 1. The minimum of this is 2, the minimum of this is 2, and the minimum of this is 4. So you take all the minimums from all the subarrays and you sum it up. So once you've summed it up, the value that you get is 17, and that is what you will have to return. The value might be very large. So the question is stating that you are given a mod value which is 10 to the power 9 plus 7. If the value is very large, you mod the value with this particular value and then return. So usually whenever you get larger answers, because you cannot store it, so what they end up doing is they do a mod so that they can trim up the value. Perfect. So how do we solve this? Obviously the brute force is clearly visible on the screen, right? The brute force is generating all the subarrays and figuring out the minimums and summing it up. Yeah, we will generate all the subarrays. So if you carefully observe, the first subarray is this much, the next one is this much, the next one is this much, and the next one is this much, which is all the 4 subarrays starting with 3. So maybe I can keep an I pointer here, and then I can keep adding elements, and I can keep updating my minimums. Yes. After that, I can keep my I here. First one is this, then this, then this. And as I go through, I keep updating my minimum and I can keep on adding. And then I here, this is this, this is this. And then I here, this will be this. So can I say, like if I have to, maybe I'll just quickly erase this so that we can write down the code. So we'll take a sum which is 0. And can I say I equal to 0 till n minus 1, because from every index we can have subarrays generated. After that, maybe I can do a minimum which is array of I. Yes, I can do that. And after that, I know the first subarray starts from, it's this much. So j equal to I. That's the first subarray. Okay. And it goes on till n minus 1. So what I can do is every time I could update my minimum. So which is min of minimum comma array of j, not I, array of j. So my minimum is updated. So what I'm very sure is I to j is my subarray. Then j goes, I to j is my subarray. Then j goes is my subarray. I to j is my subarray. So every time minimum is going to be my minimum of that subarray, because every time I add an element, I keep on updating my minimum. So what I could do is I could straight away say sum equal to sum plus minimum. And remember, in all the mod cases, you could do a mod over here. And you could probably store the mod value equal to int. And then you can write 1e9 plus 7. So that's it. So that will be it. And you could end up returning whatever is your sum. Now, what is the time complexity that you're taking over here? I'm ending up taking a bgo of n square over here because I'm running a couple of loops. What about the space complexity? I'm not using an external space. I'm using constant space. Obviously, this is the moment the interviewer will be not happy. I'll ask you to optimize the bgo of n square. So let's check out the optimal solution. So we need to optimize bgo of n square time complexity, which means we're looking something around bgo of n, right? Okay, so how do I optimize? So what I'll do is I'll go to the initial drawing table, and what we did was we generated all the subarrays, and among all subarrays we picked up the minimums and then we added it up. So if I ask you what is the how many times this particular element contributed to my answer, you'll be like, over here once, and I don't see it. So it contributed once to my answer, like it was minimum for once. So I can maybe write it in green color. It is minimum for once. Okay. How many times did one contribute to your answer? It'll be like once, twice, thrice, 4 times, 5 times, 6 times. So it is 6 times into the answer. How many times is 2 there in your answer? Once, twice, 2 times. How many times is 4? Once. So if 3 has contributed once, so I'll just add 3 to my answer. So I will add 3 to my answer. If 1 has contributed 6 times, I will end up adding 6 into 1, that is a plus 6. If 2 has contributed twice, I'll add 2 into 2, 4. If 4 has contributed once, I'll add 4 into 1, 4. And eventually, I'll get 17 as my answer. So what I did was, I broke down the problem from generating all the subarrays to finding out individual contributions and adding them up to get my answer. Okay. Is it an optimization? We still need to figure out how to find the individual contributions. So for that, we will move on to this particular example. So before we move on to this one, please make sure you know about next greater element and previous smaller element. And if you have done this, you should be able to do the next smaller element, and you should be able to do everything which is next smaller, next greater, previous greater, previous smaller. You should be able to do all the varieties. If you're not able to do this, please pause this video right now. Go back and watch the video on next greater element and try to figure out previous smaller element, next smaller element. Try to do it on your own and then come back to this one. Okay, that's the prerequisite. Otherwise, you'll not understand anything. Fine. Tell me one thing. If I ask you, what is the contribution of this particular 3 in how many subarrays will it be the minimum? You'll be like, hey, this can be an individual subarray. This can be 3, 7. This can be 3, 7, 8. Correct? But either of these 3 subarrays, in all of them, 3 will be the minimum. Agreed? But if I take 3, 7, 8, 1, will 3 be the minimum? No, in that scenario, 1 will be the minimum. So the subarrays that I can take is 3, 3, 7, 3, 7, 8. So there are 3 contributions over here that I see. But I'll not count it as of now. Maybe I can also take 3, 7. Maybe I can also take 3, 7, 6. Maybe I can also take 3, 7, 6, 4. But I cannot take beyond it. So maybe some subarrays on the left side as well. Or maybe something combining them. You never know. Maybe something combining like this. So you can combine them as well. Okay. So I know one thing for a fact. On the left, I can take all of these 4 elements as a subarray. On the right, I can take 3 elements as a subarray. Not this one, not this one. So if I can take 4 on the left, 3 on the right, what will be the total number of subarrays that you can generate? Simple maths. If this is 4, this is 3, the total number of subarrays, combining them will be 4 cross 3, which is 12. I'm not going to explain how this 12 came up. It's mathematics which is being taught in high school, so you can go back and watch it. Or you can just write it using pen and paper, you'll understand how this is generated. So 12 subarrays is what I could possibly generate. So if I could generate 12 subarrays, that means 3 is minimum for 12 subarrays, which means the contribution is 12 cross 3, 36. I could straight away add 36 to the answer. But now the question arises, hey Striver, how did you figure out that you'll have the right has 3 elements? It was super simple. What I'll do is, I'll end up writing down the indexes. The index is 0, 1, 2, 3, 4, 5, 6, 7. I ask you a very simple question for this 3. Which is the next smallest element? So if you look at this, 7 is not smaller, 8 is not smaller, 1 is smaller. So the moment you add 1 to your subarray, 3 never remains the minimum anymore. So you cannot add 1. So what you know is, for this fourth index, the next smaller index will be 7. So 7 minus 4 will give you 3 elements on the right. Okay. And if I look at the previous smaller element, this is the previous smaller element. So you end up taking this one. So if I ask you what is the previous smaller element index, that is 0. So you're currently at the fourth index. So fourth index minus previous smaller index gives you 4 elements. And then you can multiply that, you'll get 12. So all you need to know is, where is the next smaller index and where is the previous smaller index. If we're able to do this, I think we're done here. Okay, I hope you've understood this. It's pretty simple, because if these elements are greater, they can easily form the sub-arrays. So again, I'm assuming you know how to write a next smaller element stuff. I'm assuming you also know how to write a previous small element. In case you don't know, the code will be given below. Please go back and watch my next greater element video. Okay, so I think we got the gist. If I can do that for 3, I think I can do that for each and every element. Right? So just make sure, if let's say if this was 10, in that case you couldn't take all the elements. So just make sure if there is no next small element. If you see for this 3, there is no next small element. In such scenarios, please assign next small element to be n, like the nth index, so that the subtraction holds, and the previous small element to be -1, in case you don't find a previous smaller element. Okay, time to probably write down the code. So I'll write down the code and then we can discuss some edge cases. So what do I need? I need the count, like the sum. So integer, I need to figure out the sum. So I'll be given an array. Perfect. So what do I need? I definitely need a couple of stacks. One is next small element. So maybe I can say find next small element, and I can write a function for that. I'll write it afterwards. And that will give me, maybe I can say previous small element, and I'll say find previous smaller element, and I'll pass on the array, and maybe that will give me it. After that, I can take a total, which is 0, and I can take a mod value, which is typically integer, and there are 1e9 plus 7. Perfect. Time to write down the code. So what I'll do is, I'll start iterating, like I equal to 0. I'll go through each and every element, and I need to figure out how many elements are there on the left, which is typically, I can say, whatever index I'm currently at, I'll do a previous smaller element index. That's it. I'll ask how many are there on the right, which is typically going to be next smaller, because that is the greater one. Next smaller element minus the current. That will give me the number of elements on the right. So can I say the contribution will be added to the total? So maybe I can say total equal to total plus right multiplied with left. Make sure you do a 1 LL, because in case it's a long, multiplied with the value, which is array of I, because that is the contribution. And you can do a modulo. So basically what you do is you do a modulo here, and after adding, you again do a modulo. So that's how you do the modulo. After every operation, you typically do modulos. So that's done. And eventually you could end up returning what you'll end up returning, I think, the total. That is it. So all we need to do is, we need to write the find NSE and find PSE. So we have some edge cases that you will have to consider. So I'll tell you the edge cases now. Time to tell you the edge cases. Imagine I give you an array like 1, 1. So what happens is, you come across this one. So first of all, let's do one thing. Let's write down the indexes. So the indexes goes as 0 and 1. And after that, let's take some time out and write the NSE. So the next small element for the first one will be, they don't have one. So you could write the last index. This also doesn't have 1, so you could write the last index. And the previous smaller element would be -1 and -1 because they don't have 1. Okay, fine. Now let's do the contribution part. Imagine you come up to the first element, which is the 0th index element. So when you're at this element, you say, how many do I have at left? He says, I don't, like typically 0 minus of -1, which is, I have one element. Okay, which is he himself. Okay, on left I have 1. So I'll write that 1. How many do I have on right? That's typically the 0th index and the second index. So 2 minus 0. I have 2 elements, which is correct. I have 2 elements on the right. So write as 2 elements. What is the contribution? Twice into 1. So I'll add twice contribution. And typically those subarrays are 1 itself and 1 comma 1. Like 1 itself and 1 comma 1. Perfect, done. After that, I move to the next. Now the moment I move to the next, I will get some different numbers. And that will be, left will be 2 elements and right will be 1 element. You could do that yourself. And the contribution comes out to be this. This time, the subarrays that are considered is this, which is 1. And then there is this, which is 1 comma 1. I will be like, hey, wait. You already considered 1 comma 1. Why are you again considering 1 comma 1? So you'll have to be very sure. If you're considering from here, don't consider from the back. So you could do either way. Either you consider from the back and then you don't consider from the front. So you can only consider it once. So what you could do is, you could probably consider it in the front, which is typically saying the next smaller element is correct. And you don't consider it on the back. Now what this means is, when you're looking for previous smaller element, over here, when you looked for previous small element, you didn't find one and you wrote -1. Instead of it, you end up writing 0th index. What you're saying for this one is, this is my previous small element. So it boils down to not previous small element, this time previous smaller or equal element. So when you do this, the left comes out to be just 1, because the previous smaller element will be updated and that updated value will be 0. So this time when you take the index 1 and you say previous small element 0, so you'll get the left to be 0. So you'll end up just taking this one. You'll just end up taking this one. Got it? Previous smaller equal, so that you don't consider 1. You don't consider the equals. Perfect. So now we know how to handle the edge case. So you have to figure out how to write a code for NSE. I'll have to figure out how to write a code for previous smaller equal element. So PSEE. Got it? Remember, previous smaller or equal element. Okay. So first I'll try to find NSE. So we'll have to return a list. So list of integer is what is returned, and I'm writing find NSE. Remember, I need the next smaller element. So I'll take the array. What do I need? I need a NSE of size, like a list NSE or an array NSE, whatever you can take, of size n, and I need a stack st. Post it, what we can do is, because we are looking for next smaller element, so I can traverse from I equal to n minus 1 till the 0th index. Perfect with this one. What after this? We will check the straightforward, the next create element stuff. We'll check if the stack is non-empty. Okay. And we will be like, we'll be storing indexes in the stack because we need indexes. Why do we need indexes? Because we are subtracting indexes. We don't need element. We need indexes to be stored. So I'll be like, okay, if indexes is stored, I will compare that with the array. So array is stack dot top. And I'm looking for next smaller. So anything that is greater or equal is what will be taken off. Which is pop. Okay, done. I've taken it off. What after this? I'll say NSE. Now either if the stack is empty, please assign n because I'm looking to assign n so that the subtraction is done. Otherwise, assign whatever is at the stack.top. At the same time, please make sure you add a stack.push, the index, not the array element. And the for loop is done. Please make sure to return NSE, and that will be the find NSE stuff done. Okay, perfect. I go down and I try to write the PSEE list again. Find or compute, whatever you want to write, NS or rather PSEE. Again, I'll end up taking an array. This time I'll require PSEE of size n. I will require a stack ST, and I'll start traversing from the front because I'm looking for previous n minus 1. What I write is while the stack is non-empty, at the same time, please make sure array of stack.top, I'm looking for smaller. So anything which is greater, I'll not remove equals element because I'm looking for smaller or equal. I'll just remove the greater ones. Array of I. Please make sure you pop them out. And once that is done, you say PS EE of I. If the stack is empty, please store -1 or else whatever is at the top. And once that is done, please end up pushing I to the stack and the for loop ends, and you could end up returning PSEE, and that will be end with the list function. So yeah, that is what it is. Time to compute the time complexity. So this computation, next creator element works in bgo of 2n with a space complexity of bgo of stack, which is bgo of n. Do I need anything else? Yeah, you're using a stack inside, so bgo of 2n. Same for this one, where you compute PSEE, and then this one is straightforward bgo of n. So I can say that the time complexity is somewhere around bgo of 5n, and the space complexity is somewhere around bgo of 5n. Yes. Why 5n? Because I'm using an NSE, a PSE, a couple of stacks, one here, the other one here, but this is all modularized code. You could probably do better. You could make 5n, 4n, or maybe 3n, but we'll not focus on it because writing clean code is very important. And if you're going in an interview, try to write code like this. This is where the interviewer gets super impressed. And yeah, this will be the most optimal solution unless until you decide to optimize this to 4n. So yeah, that will be it for this one. So if you're still now watching and if you've understood everything, please do consider giving us a like. And if you're new to our channel, do consider subscribing to us as well. With this, I'll be wrapping up this video. Let's meet in some other video. Till then, bye. Take care.
Whenever your heart is broken.